Okay, Takhya.
Hi, I'm Takhya. I'm a senior at the University of Texas at Arlington. I'm studying chemistry. So this summer I was at the University of Bayreuth in Germany working under Dr. Motz. I worked with Bernardo Silva. He's a PhD student. So this summer we worked with SiCN titanium dioxide ceramic fibers for visible light driven hydrogen generation. So the demand for hydrogen generation, for hydrogen energy has grown since the 70s, but hydrogen only accounts for about 6% of energy produced globally. So investments have increased, but it still remains low, with its peak being in 2008. So for this project, we worked with water electrolysis. So essentially water splitting, which only accounts for 0.1% of global hydrogen produced, but interest is growing due to its decreasing costs. So the goal of the project was to create a better catalyst a catalyst that is effective under visible light. So the typical methods for hydrogen production are biological, thermochemical, or electrolytic, with thermochemical being the main. Commercially thermochemical methods are predominantly used. So typically steam methane methods, where they split hydrogens from methane, but this process leads to carbon dioxide emissions. So Bernardo wanted to focus on electrolytic methods, which have no emissions or byproducts, where we were working to split water using these SiCN titanium dioxide catalysts and visible light as our solar energy source. So these photocatalytic processes are essentially where a semiconductor is illuminated with an electromagnetic source greater than its band gap. And excuse me. Then this band gap, and electrons will move from the lower valence bands to the higher conductance bands where it can participate in conduction. So we were interested in visible light, specifically the extension of visible light absorption. So we wanted to work with a catalyst. We needed our catalyst to operate at a band gap less than 3 electron volts in order to be effective under visible light. So he worked with specifically SiCN supports for these catalysts, specifically because silicon-based catalysts have been found to improve the activity compared to traditional catalysts, and they offer properties such as extension of absorption of visible light, degradation of organic dyes, and purification of water, where it has already been done with SiCN titanium dioxide composites, where they have the ability to extend photocatalytic activity towards visible light. So Dr. Motz did not want me to include exactly what we did experimentally, but I'll give an outline. So we started with a precursor, which we doped with a titanium source. We electrospun fibers, and then we cross-linked, pyrolyzed, and then we started the characterization. So this summer, I mainly produced fibers. I made some bulk samples so that we can do the characterization steps. We did FTIR, XRG, Raman, FTIR. Those are the ones that we've done so far. And I was only able to show some of the SIM characterizations, where this image here has no titanium, and then we increase the titanium as you're moving in this direction, with this having the highest amount of titanium. So right now, Bernardo is working on the VET surface area analysis, and NMR And then once he returns to Brazil, he will do the UV vis diffuse reflection spectroscopy. And then he has decided to finish his PhD dissertation first, and then he will start his hydrogen generation test after that. Sorry, it's pretty short. Any questions?